All right, so after I calculate my test statistic, I need my degrees of freedom. And so from yesterday, what we talked about, our DF is equal to K minus 1. So again, our K here was the number of categories. So there were 3 different outcomes, winning, losing, and tying. So our degrees of freedom here is going to be 2. So now I need to take these 2 values and I need to go to my chi-squared table. So I'm going to go to my table and I'm going to look in the second row here. And I'm going to look across and I'm going to see, okay, where is 5.25 going to be between? That's going to be between these 2 values here. So 4.61 and 5.99. So that means that our p-value is going to be between 0.10 and 0.05. So our p-value is between 0.05 and 0.10. Our alpha in the problem, however, was 0.01. So our p-value is going to be greater than our alpha. So then we fail to reject our null. So now, after this problem, I can go ahead and do my classwork. But I do want to go over one more problem together, just because sometimes it's not going to be with equal frequency. There's going to be percentages that are in the problem that indicate what's or what the percent of time we would use for our expected value. So I want to go over a problem like that. So let's take a look at this example here. Let me see if I can move this up. No, I cannot. Okay. So we're going to take a look at this example here. So Avery noted that in the previous year, 50% of patients who worked at the clinic had 0 to 15-minute wait time. 30% had 16 to 30 minutes, and then 10% had 31 to 40-minute wait time. So she wondered, and then 10% had 46 or more minutes. She wondered if the patient's wait time were still following this distribution. So she took a random sample of 150 patients and recorded their wait time. Here are the results. So this is going to be a little bit different than how we calculated the expected value before, because now we are dealing with different percentages, not equal frequencies. So I'm not going to use the total observed values and then divide by the number of categories. That is only when we have equal frequencies. Since there are percentages given in the problem, I'm going to use those percentages to figure out how many I would expect. So I'm still going to take my n value. So now to calculate the expected value, let's actually do this for the 0 to 15 minutes. I'm going to take my n. So here I'm going to take the 150 as my sample, and then I'm going to multiply the percent. So 50% here is the expected wait time. Or we would expect 50% of the patients to wait those 0 to 5 minutes. So this is going to be my expected value for this problem. So here we would expect somebody to wait 75 minutes, we'd have 75 patients waiting 0 to 15 minutes. So that's my expected number of patients. For my expected value for the 16 to 30 minute range, I would have the same n value, 150, but now I'm multiplying it by 30% to get my expected value of 45 patients. for the 31 to 45 minute wait time. Again, we take our n value, the random sample, and we multiply it by the 10%, since we think 10% of patients wait between 31 and 45 minutes. That'll give us 15. And then our expected value for the last one here, for the 45 or 46 plus minutes. Again, take our n value, and now we're multiplying by 10%, since we would expect 10% had 46 minutes or more. So these are going to be our expected values for our formula, but our observed values are still the ones in the table. These are the observed. So when I'm calculating my test statistic, I'm not going to have the same expected value for every single term in my equation. So now I'm going to calculate my test statistic using the formula that we did before. So we take the observed for the first value in the table, 75, minus the expected, which we calculated as 75, and then divide by the expected. So plus 55 was the observed, minus 45 was the expected, over 45 for the expected, plus 15 was the observed for 31 to 45 minutes, minus 15 for the expected, over 15, plus the 5 for the observed for 46 minutes or more, minus the expected, which was 20, or excuse me, expected was 15, over the expected 15. And if I crunch that out, I should get 8.89. And then again, I need my degrees of freedom. So my DF here, we have 1, 2, 3, 4 categories. So 4 minus 1 is 3. So again, I need this value here and this value here. So I go back to my table, and let me erase this here. This is from our previous problem. And I look in the 3 row, and I look across where is 8.89. So that's going to be between here and here. So I go to the top, and so my p-value is going to be between 0.05 and 0.025. And our alpha was 0.10. So that means that our p-value is definitely less than alpha, so we reject the null. We actually did not write our hypotheses or do the conditions, so let's do that now. Apologize for jumping in there too quickly. Here again, even though we're dealing with frequencies here, we're essentially going to say the observed is still equal to the expected. Our expected are just calculated a little bit differently. But we're still trying to say we think that our observed value should be equal to the expected value. And similarly, we think that maybe the observed is not equal to the expected value for our alternate. And then secondly, for our conditions, it said we took a random sample right here, so we're good there. Each of our counts, our observed values, were definitely greater than 5, cutting it close, greater than or equal to 5, excuse me. We're cutting it close there with the 45 plus, but we're good to go there. And then our random sample was 150. Let's assume that there are a large number of patients, so we are good to go there. So now we know which hypothesis we are actually rejecting, so we are done with this problem. All right, so please make sure you are going to Google Classroom and submitting hopefully by 9 o'clock. If you don't finish by 9, you can submit by 4 p.m. at the latest. I will be available on Zoom until 9 if you have any questions. All right, have a great afternoon, everyone.